a shakuhachi, Japanese fruit.
Ich hatte meine Textquelle, ich wollte nicht verlieren. Ich habe tatsächlich einen Text jetzt für mich gerade gekauft. Weihnachtsgeschenk. Ich hatte dieses eine, ich glaube, es war ein Ich will jetzt unter die Stadt gehen, die Stadt ist komplett ja, immer ging das hin. Rechtzeitig. Richtig.
Okay, last lecture this calendar year. We're in the place called the Promised Land, absolutely gorgeous hinterland of the north coast of New South Wales. Lots of rain, as you can tell by how green it is. So today we're going to talk about the construction of data and distributions. Remember last week I just focused on data. What do we do with data? We construct distributions, and we'll talk about a range of things as usual. This notion of theory-ladenness, which it's a term from the philosophy of science about this. The idea is that there's no such thing as just raw observations. There's always a theory in your head, and I will consequently argue that data is actually a construct. It's helpful. Normally we think of data as a thing that's out there in the world rather than something that we've gone and built. I will try and argue why it can be helpful to think of it in this rather opposite direction. In particular, probability distributions, which we use pervasively when we theorize about machine learning, like when you develop a new algorithm or you try and argue how well the algorithm is working. You always appeal to the distribution of the data, but that itself is a construct from the data. We'll challenge the notion of the normal, as in the normal distribution, with an interesting example, and it gives me an excuse to show a picture of a nice beach. And we'll meet the reference class problem again, we've already met it, as a warm-up for the first lecture next year. And I'll very briefly allude to causality. So theory-ladenness of data. So it's not really a stretch to argue that the kind of the crude philosophy of a lot of machine learning is very much aligned to the way many people used to think of science, this thing called logical positivism. We don't have to worry exactly what that is, but a crucial aspect of it was that you wanted to just observe the world as it is. People talked about observation sentences, really primitive observations. The idea was you didn't go and have some theory in your head, some prejudices before you went and looked at the world. You'd look at the world as it is, you measure that, and then by induction or some magical process, you then go and figure out what's going on. And it's still it's funny, in the philosophy of science literature, it's roundly rejected. I mean, this was popular in the 1930s. You know, I don't think any philosopher of science would buy it for a moment now. But you look in other disciplines, biological systematics, or in economics, for example, it's still there. People still buy into this a lot. And it's unviable because no matter what you observe, there's always some theory in the back of your mind to make the observation. Like if you're going to go and measure a voltage, there's a whole stack of theory about electricity, about how the voltmeter works. There's no such thing as a direct raw measurement. And all of our data has this property. So there's none of these basic statements that are somehow theory-free that just gives you, the raw facts of the world. Anyway, so if you're interested with a philosophical bent, you can look at this. There's a article in the Stanford Encyclopedia of Philosophy that, gives you a good entry point. This resource, by the way, is useful. If you ever come across some philosophical concept, these articles are, I guess the only problem with them is they're very long, but they're structured and they're ordered, and it's a good starting point to go to, better than Wikipedia. So let me get more concrete about the theory latedness of data. So a couple of quotes from some philosophers of science, both women as it turns out. Helen Longino, the naive fantasy that data have an immediate relation to the phenomenon of the world, that they are objective in some strong ontological sense of that term, that they are the facts of the world directly speaking to us, should be finally laid to rest by the papers collected in this volume. So there's this whole book, which I can't even read. I made it so small. Data Journeys in the Sciences. But anyway, that's the essence of what she said. And here's a more long-winded quote from another philosopher. So this is from a paper, Towards a Taxonomy of the Model Latedness of Data. So if you call it theory latedness or model latedness, it's much the same point. I will let you read that in full, but note the last sentence here. While this folk view has been challenged by philosophers of science for a long time, it still often shapes our thinking about data. So my point of giving these quotes is to say, it's not just my view. There's at least 3 of us that think this. I think there's actually a lot more people that would have this view. And it's not an idle academic point, right? So that's what I want to make that's the point I want to make now. So quite some years ago, so when was it? 2008, in Wired magazine, I think it was, there was this article that caused quite a stir. The End of Theory, the data deluge makes the scientific method obsolete. So the argument was, you go and look at the way science is done as a way of understanding the world. You have all of this complicated theory and maths, and oh gosh, that's so difficult. Wouldn't it be great if we can just get computers to find the correlations, and really that's all there is to it. And that's what this ridiculous article claimed, right? It was really, I don't know, you can read it. It's kind of funny that it's so histrionic. So that was 2008, but it keeps coming back, right? So this was January 2022, so just under 2 years ago, in the Guardian. Yes, in The Guardian. Are we witnessing the dawn of post-theory science? Does the advent of machine learning mean the classical methodology of hypothesize, predict, and test has had its day? Right? That's the question they ask, right? And the good thing is, I've been careful not to give you answers in this course very often, but I can tell you the answer to this one is no. It's just silly, right? It's and the big silliness is that, the presumption in this question is that these methods, like just analyzing the data, are somehow theory-free, right? That's the thing that they're missing. And so that's what we're going to talk about today, amongst other things, criticizing this idea that the data-driven methods are essentially theory-free. And to be a little mean on it, you can, so there's this famous Russian psychologist Lev Vygotsky, who wrote this very famous book called Thought and Language. And he talked about this idea that if we could just measure stuff, we don't need theory, right? We just measure the correlations. So you give a name to that, and it's called naive empiricism. Empiricism is looking at the world empirically. Naive empiricism, as he says, it's the absence of a system, merely making empirical statement of facts, right? You're just observing. Anyway, he points out that we all go through this phase when we're little kids, right? So that's, if you wanted a psychological theory as to why this keeps coming back, it's because each child discovers this. Now, fortunately, some of us grow up and realise that you have to go beyond that. But I think those newspaper articles I pointed you to before, Vygotsky would say, well, that's just the 5-year-old talking. I don't think I'm being unfair. So this idea, it's got various names like Dadaism. There's this crazy art movement in the 1920s called Dadaism. There's a funny, I don't know, the words are similar, right? But Dadaism, right, as per this paper I found, datafication, Dadaism and data valence, big data between scientific paradigm and ideology. A lot of big words here, I realise. Dadaism thrives on the assumption that gathering data happens outside any preset framework, as if Twitter facilitates microblogging just for the sake of generating life data. Anyway, I think you get the point. And yeah, I don't think I need to say that. So there's issues like, the measurement scale, your instruments and so on, like I already alluded to. But one of the things I wanted to particularly draw attention to, precisely because it's so invisible normally, is this thing which I'll just call choice. There's a theory-ladenness in what you choose to measure. This is not so obvious to you, right? Unless you reflect upon it. So there's this nice quote from Chaim Perelman. We met him before. The choice of facts deemed relevant, choice of hypotheses, choice of the theories that should be confronted with the facts, and choice of the actual elements that constitute the facts. Once you start thinking in these terms about all the choices that you make when you gather data, you realise there's a lot of theory there. Right? So try and translate this to some practical example. You're going to go and gather some data about people to make some socially relevant prediction. Whose data are you going to get? Maybe you're interested in something to do with lending practices. So you'll say, oh, well, I'll just gather data from bank customers. But what about all the people who don't have a bank account? Because they weren't allowed to have one because the bank thought that they weren't a good risk, right? You've just got that selection bias that we met in the previous lecture. This same idea we actually met in a previous lecture. Remember when I told you about this book published by the CIA, The Psychology of Intelligence Analysis? Richard Hoyer says there's no such thing as the facts of the case. There's only a very selective subset, right? It's what you choose to measure. So, first main takeaway from here, the most significant theory is the one that guides you in choosing what data to measure and what data not to measure. And let me stress the data that you didn't measure. So there's a nice metaphorical name you can give to that I like to give. So there's a Sherlock Holmes book. I can't remember which one it was, but here's the dialogue there. So there's a detective. Is there any other point, Mr. Holmes, to which you would wish to draw my attention? Holmes says to the curious incident of the dog in the night time. The inspector says, but the dog did nothing in the night time. Ah, says Holmes, that was a curious incident. And in the story, this was quite relevant. So the point was, there is a dog. The dog is renowned to bark all of the time. There was an intruder. A crime was committed, but the dog didn't bark. So what does Holmes conclude from that? That the dog knew and liked the person who came. But the thing is, clever fellow, right? He noticed what didn't happen. It's much harder to notice what didn't happen than it is to notice what happens. So that's why I make a deal of this and give it this metaphorical thing so you can now remember it. Always watch out for the dog that didn't bark. I made that point, and got to have a picture of very dapper looking Basil Rathbone. Okay, so another slightly unusual perspective, perhaps, is this idea of data as a construct, right? Something that you actually make yourself. At first sight, it seems ridiculous. Surely data is the very opposite of something that you construct. I mean, sure, you construct your model, you construct your predictions and your actions, but not the data itself. So, etymologically and historically, data means to most people that it's just given to you. It's a direct representation of the world. It's a fact, right? Like I said in a previous lecture. I'd already introduced this other word people have coined called CAPTA, which captures the idea that this information, you actually select it and take it, right? So this is capturing that notion of you choose what it is that you measure. So it's acknowledging the element of a choice, but it's still a representation of the world. It's out there, right? I'm choosing to go over there and get this, right? And it's very clear in your head that, this is not you, this is the world, right? Which, this is a perfectly reasonable way of thinking about things. But the slightly bizarre notion I want to flag now, just as an alternate way to think of it, and to make up my own clunky word, constructor. Data as a construct, both based on the world, but unquestionably the result of the world. And this is not as crazy as you might think. So there's some literature on how science works. So two very famous books, one by Bruno Latour called Science in Action, and the other one called by Ludwig Fleck called The Genesis and Development of a Scientific Fact. Now this latter one is one of these books with such an intriguing title that I had to read it. When I came across this, I thought, what on earth could that possibly mean? And how could you write an entire book on a single scientific fact, right? And what does he even mean by the genesis and development of it? So if you do ever go and look at that, you'll find that he talks about a particular thing. So it's a thing called the Wassermann reaction for detecting syphilis, right? It's a particular disease. And the question is, how can you tell whether someone's got this disease or not? Nowadays, everyone accepts this, right? It's like it's in textbooks. Medical students would learn it. Oh, if you want to detect syphilis, you use this thing, right? What is that? That's a fact, right? Everyone accepts it. No one questions it. It's rock solid, right? What the book traces is how we collectively went from no one believing that thing was even possible through to, one guy figuring this out and then trying to persuade everybody that it was so. So it became this very gradual process. So it's not like this fact just appeared. People had to work very hard at it. Likewise, in this other book, which I think is cool, Science in Action, compared to most books that talk about science, which take this, rather grandiose and theoretical notion of how science is supposed to work, what Latour did in this book, so he's an anthropologist, he studied scientists as an anthropologist would study members of an African tribe. The anthropologist goes out and lives in the bush and watches the weird rituals, what they do when they go farming or hunting, their mating rituals, all of that stuff. He did that in a laboratory in California. It's really cool. It's very, very interesting. He paid particular attention to what the scientists did rather than what they said they did, right? Normally, all the books you read about science, it's what people say. He actually looked at what they actually did. So that was quite an inspiration for me in crafting this course about, trying to think of what we actually do. Anyway, and as is surprisingly often the case, the truth is hidden in the etymology of all of this. So this idea of a fact that I introduced in a previous lecture, if you look at the etymology of it, the clue of a fact's production is in its etymology, since the Latin factum is the neuter past participle of facere, to make. Facts are made. It's there in plain sight, apparently, if you knew Latin. I never knew this. There you go. So I guess, some of you must have studied Latin in school. It's still a thing here, not in Australia. And you always wondered how it's going to be useful. There you go. So with this view that your data is constructed, you can now ask questions that you couldn't have asked otherwise. That's my point of introducing this. You can ask yourself, how was the data constructed? By whom, for what purpose, and why? Right? It wasn't just given to you. There's a nice analogy that I found, and a very interesting paper. Again, it's one of these things that you think, surely that cannot be exciting, like a paper on the history of the development of accounting, right? I mean, accounting is already seriously boring, right? History of accounting, you'd think doubly so. This is a really cool paper, right? And he starts off referring to a picture. So in the PDF of this paper I shared on Moodle, the image is all munged, right? It's like been through a photocopier 6 times. So here is the clear image that he's referring to. And he starts the paper referring to this quite famous drawing by Escher. And, the whole point of this is that you're messing with the usual subject-object distinction, right? Normally you think of the artist is like, I'm the artist, I'm here, I'm looking at the world, I go and depict the world. Here's the artist looking in a spherical mirror and he's depicting himself. Okay, nothing profound about this, it's just a mirror. Okay, he's a very clever draftsman to draw a picture that elegantly, but the author of this paper, Accounting as Reality Construction, essentially makes an argument analogous to the one that I've just been making. You just have to replace machine learning by accounting. You see what he writes. The idea that accountants represent reality as is through the means of numbers that are objective and value-free has clouded the much more important insight that accountants are always engaged in interpreting a complex reality, partially, and in a way that is heavily weighted in favour of what the accountant is able to measure and chooses to measure through the particular schemes of accounting to be adopted. You can literally translate that directly to machine learning. Okay, I think that's all I need to say about that. So I alluded there to values, and I've already used this phrase, theory latentness, and so then you can ask, well, what's the transition to the idea of value latentness? And so if we just set aside the theory latentness explanation, so there is this famous paper by this philosopher, Hilary Putnam, called The Collapse of the Fact-Value Dichotomy. And I guess in general discourse, we tend to think that, facts, these solid things about the world, about the objective reality, they're about as far away as you can get from things like values, right? Ethical precepts, things that you hold dear to your heart, right? They're quite different things. You've got different words for them. And his argument in this paper is that apparent distinction is nowhere near as clear cut. So we face the same problem when we look at machine learning systems. We can go and think that, well, I'm just measuring data, right? So the example I gave before about, who's eligible for a bank loan. I'm just looking at the facts. I'm just going to go and look at whether or not people have repaid their loans previously. That's about as objective as measure as you could get, right? I'm just predicting on the basis of past behavior what's going to happen in the future. I'm not imposing my values, right? I'm just being objective about it. But of course, you are in a way, because you're implicitly assuming that anyone worthy of getting a bank loan already has had a bank account, right? But how does this start off, right? I mean, normally it would start off by having parents who are rich enough to be able to, grease the wheels for you, open a bank account when you're in school. So, all of those things, you can elaborate this story yourself, I'm sure. But it should not be hard for you to go and, dream up scenarios where you're predicting something on the basis of data that's something to do with people, and there are going to be values encoded in what you choose to measure. So that's the point I want to make here. And these two things, the value ladenness and theory ladenness, right, they sound like they're somehow similar. And again, looking at the way Shane Perelman thought about this, he essentially argues that they end up being the same thing, right? Your values, you can think of the values that you have as a theory of the way the world should be, right? So if we wanted to, we could just use the same word for both. It's convenient to have the two words because we tend to think of theories, it's about physics, the way projectiles move and so on, and values are about ethical concerns. But in his book on how we make reasoned argument, how we try and persuade people, in other words, rhetoric, he says, essentially he argues that values are a theory. And I don't want to make too big a deal about that. I guess all I'm saying is that if you accept the notion of theory ladenness, I think you should also accept the notion of value ladenness. And this affects the data that you might measure. So what are the implications of these very general points for machine learning? So the data that we use in a machine learning system is inevitably going to be imbued with values, and it might not be manifest. And it can be very difficult to excavate what they are. So there's a paper I've pointed you to that gives you maybe some insights on that. Our whole exercise in this course has been grappling with ethical dimensions of machine learning. It's the very intersection of this very facty view of the world and our values. So we have to worry about the intersection. And what I'm telling you now, like Hilary Putnam's point, is that actually these two worlds are not so clearly separated. I've already made this third point that we need to evaluate things in terms of their intended use. There's no universal method that will fix this. And all of these concerns, like these difficulties that I'm pointing out, that, your choice of data is laden with your theories, it's laden with your values, it's all contingent, it's not certain. Yes, that's all true, but I'm not saying that therefore it's a terrible idea to go and use this, right? It's like, there's only one thing worse than using data, and that is not using the data. Here, all I'm trying to get across is some of the non-obvious headaches that you will encounter. Anyway, that's all very highfalutin in general, I realise, and maybe doesn't appeal to all of you. Let's get a little more concrete and more directly tied to machine learning practice and talk about distributions, probability distributions. So if you buy the argument that data is constructed, then it logically follows that its downstream products are as well, right? Because you make the downstream products out of the data. And the key point why focus on distributions, as I think I've already mentioned, machine learning doesn't just work with garden variety facts, it works with statistical facts, like probability distributions, right? These aggregate claims, right? That the average height of people in the front row of the class is such and such. It's not necessarily about an individual. So that thing, that mathematical object, that distribution is a thing that we build. Now, there's two aspects of this. One is the choice of groups. Do I do it row-wise or column-wise? Do I do it by sex? Do I do it by height? There's many different ways of slicing and dicing. We'll come to that again later in the lecture on the reference class problem. And the whole next lecture will be focused on that question. So we set that aside for now, but there's still, once we've fixed the groups, there's still a question of constructing a distribution. Now, at one level, this is just a triviality, because we can say, if I've got some observations x1 to xn, just think of them as numbers, right? That's my raw data. Now, of course, I can represent that as an empirical distribution. So imagine you've seen this as a standard trick, right? So delta sub xi is the probability measure that puts all of its mass at xi, right? The Dirac delta. So this is just a way of writing it's called the empirical measure. There's no other one, right? It's just the empirical measure. It's stock standard. And the thing to observe is that if I give you this set, then Pn is uniquely defined and vice versa. So it's just a change of notation. You can say, I've got this data. I can say, oh, I've got this empirical distribution. So what's the issue? It looks like there's nothing, there's nothing exciting going on here. I said at the top of the slide, it says, the distributions are constructed. Well, isn't this a construction? What's missing? What's missing is that actually we don't stop with this, right? The theory, right? The implicit theory that we always have, we have to make all the claims and the development of the methods that we've got, is that we don't just work with this Pn, we posit that Pn is somehow a good approximation to some underlying distribution P, right? What I've got are samples from that distribution P. And then any claim that I want to make, like a policy, right, where I choose to act in a certain way, or I want to go and infer something about someone, it's always couched in terms of that P, right? Each of you is a sample from the distribution of people currently living in Tübingen, right? But we can never get our hands on that directly. We've only got this indirect way of looking at it. So again, you might think, what's the big deal, right? I mean, isn't this standard? Didn't we cover this like in, first year of your undergraduate degree with your, just standard law of large numbers and so on? One way of identifying the assumption behind this is that essentially you're assuming that this limit exists. So normally, the usual argument about what the probability, just the unadorned P, what that is by definition this limit. I take more and more samples, and this Pn, this empirical measure, converges to the true measure. Now, often it does, right? It often does, but it doesn't always, and you can't guarantee it. So this is, for many situations, this point is perhaps not so relevant, but I think in some situations it becomes extremely relevant. Right, so as I said, it's usually just assumed, and how do you justify that assumption? You appeal to the law of large numbers, which is a mathematical theorem. It's not a claim about the world, right? So that's the kind of the sleight of hand here. It's a true theorem, but that doesn't mean that it applies to the world. And there's various ways that people think about how this might break, right? So I'm going to show you one of them because it's easy to understand, but I don't think it's the most important one. But it's nevertheless, I think, relevant for the ethical concerns that we're interested in, and that is the idea of an outlier. And so there's an interesting paper by this guy, William Kruskal. He's a famous statistician, if you're interested in this. Now, these outliers, they do not, the existence of outliers doesn't kind of falsify the presumption of a stable distribution, but it does cause problems. And people have grappled with it directly when considering questions of fairness. So I did a really cursory little bit of research on Google Scholar to find a couple of examples here. Here's one, FAIR OD, Fairness Aware Outlier Detection. This is just a, kind of photo of the first part of the paper. They're introducing all of the notation. And then they say, we've got this base rate, and they introduce these probabilities, all right? So I'm just picking on this as an example of what's normally done in machine learning. You say, I've got this data, and now this thing here. Now, nowhere do they say where this P comes from. They're essentially just assuming that it exists. Here's another example, right? I thought, okay, maybe I got lucky on the first go. I picked another one, deep clustering-based fair outlier detection. By the way, this illustrates the word salad of machine learning research paper titles, right? You basically get all of the adjectives and nouns that are popular, you string them all together, and that's the title of your paper. I mean, don't laugh. People actually generate there was a program written years ago to do this. You want to come up with a title for your paper, you just hit the button, it'll generate a title for you. Anyway, so in deep clustering-based fair outlier detection, same deal, right? Suppose we've given our data points, sampled IID from underlying distribution. So that thing, is, does machine learning spell the end of theory-laden science, right? No, because there's your theory, right? It's all just hidden in those few words. And to be fair, right, I thought I've picked on other people. I can pick on my former self. So 20 years ago, I wrote a paper on outlier detection. And here's what I wrote. Suppose you're given some data set drawn from an underlying probability distribution, right? I think this is the first sentence of the paper, right? Get the theoretical assumption out of the way real fast before anyone notices, right? And then you dive into the fun stuff. And then there follows 20 pages of, clever algorithms and what have you. Okay, hopefully you get the point. So, so this notion that there is a distribution, right? I said, essentially the distribution is the limit of the empirical measures. And so assuming that the distribution exists essentially is assuming the limit exists. Or more precisely, you're assuming that the relative frequencies, that is what the empirical measure asserts about particular events as n goes to infinity, is stable, right? Saying the word stable is the same as saying that the sequence has a limit. And what's curious is that this is so little studied. So the theory of probability and statistics was, as I've mentioned before, developed to try and understand games of chance. You go to a casino, the relative frequencies are very stable, because if they're not, the casino goes bankrupt, right? They're the idealized examples. So the question is, do natural phenomena, the stuff that we find in the world, do they exhibit this stability? And very few people ask that question. Now this guy did. So there's a whole book on this question, the statistical stability phenomenon. I got to say, this is not a great book. It's good that he did what he did, but it could have been done a lot better. What he did do was he specifically went looking to see whether these relative frequencies were stable. And the point is, you're not going to see that if you don't go looking. If you just presume that the limit exists, what are you going to do? You're going to go and gather your data, right? You've got some large n, you'll go and do your calculations. You'll never check whether they were converging. You'll just go ahead and use it. So I say here, many natural phenomena do not have stable frequencies. What would be an example? Anything that's not in equilibrium. So in statistical mechanics, right, so the way you can mathematically describe the behavior of a gas in a room or something or other, all of that physics works perfectly in an equilibrium situation. You've closed all the windows, the gas is here, it's settled down, there's no heat sources or anything, it's just sitting there, dead, right? And you can describe that very, very well. Non-equilibrium situations are much, much more difficult. But now you go and think of where are the problems that arise in machine learning as applies to people. It's in situations, in societies that are not stable, right? Think of a society that's stable. I don't know any. Things are never stable, right? Newspapers would go out of business. There'd be no change. There's always change. So you have that problem. Anyway, it's got some examples. I think all I wanted to say about this is that if you go looking, you can find examples for this. In the machine learning community, this problem does crop up, but they give it a different name. It's got various different names. So one of them is covariate shift. Another one is data set shift. So the way that's described is I've gone out, I've trained my model, right? I had my training data, I trained my model on this. I trained my self-driving car in the streets of Tübingen. And then I air freighted the car to Tucson, Arizona in the US, which is very, very different. And I let the car loose and it starts driving over people because everything's different. And the explanation would be, oh, well, that's because the test distribution is completely different to the training distribution. That's the way it's normally framed, right? If you go looking, you'll find a lot of papers on this, right? This is a big topic in the machine learning community. But here's the interesting thing. when you go and say, oh, the training and test distributions differ, I can equivalently say, oh, well, maybe there isn't a stable distribution after all. It's just a different way of saying the same thing. All right, we have a short break. I hope to make up for going over time last week by going under time this week. So on average, I'm on time.
Ich habe meine Schallplatten
Eigentlich, ja, wir können uns schon noch dann mitleben dann so.
Yes, you have the attention to it. Das zum ersten Mal eine Lücke. Ja. Und das ist halt keine Masse. Das muss man noch ein bisschen weiß zeigen, dass man vorne verstanden hat. Und du hast ja Kohle, kann man beschreiben, also eine Testdauer gemacht oder so.
Also nicht so, dass du das hast.
Ja, nee, ja, okay, wir wollen mit den Personen, immer Informationen weiter. Oder dieser Maschinenbauer, der viele Maschinen hat.
Was heißt das? Maschinenbauer?
Ja, wirklich. Ich habe ein bisschen Eindruck, dass der Maschinenbauer Leute, die da mit der Distribution oder was erweckt. Oder ein Goldmine.
Ach doch, Goldmine.
Okay, so what's at the beach? Easy question. Sand. Right? Lots of sand. Yeah, that's a typical Australian beach. Looks good, huh? I've already alluded, I think, somewhere in the course about when we think about data from a machine learning perspective, it's a mass phenomenon. We make these mass measurements. This is really just, in a way, a bit of an aside that I think you will find interesting, motivated specifically about sand. And I mean, there's a nice story to this. So I came across this when I was an undergraduate. It was a really hot day. I went into the library because it was air conditioned, and I just picked up this journal and flicking through it, and I found the paper that I'm about to talk about by this fellow, Rafe Bagnold. So he was a major in the British Army in the 1930s, and he was stationed in North Africa, and his military duties didn't keep him that busy. He had a science education, he had a degree from Cambridge, and so what's a fellow going to do in his spare time, right? He's in a place like this, right? This is them travelling from one spot to the other. He's a scientist. What's he going to study in the Libyan desert? Sand, right? Because there's a lot of sand. So he ended up becoming the world expert on sand, elected to the Royal Society for some of the stuff that I'm going to describe to you. There's a nice documentary about his work, if you're interested. I think it's kind of cool. What he did, I think is really cool, and it's kind of, I think it's relevant to our considerations. So this is from his paper, this graph here, the size grading of sand by wind. So what he's interested in is, okay, there's sand, right? There's lots of it. It all looks the same colour, but at least there's one thing that's different. The grains can be of different sizes. So he went and built a machine to go and measure the size of the grains of sand at a very large scale. Like, he had a lot of data points. And he would do things like he would plot distributions, right? So this is a probability density. And I think the solid line is the actual measurements that he had. And then the dotted line is the idealized normal distribution. So if you think of the arguments that you're probably told in your statistics course, the normal distribution or the Gaussian distribution, it often arises, the argument is the central limit theorem, and it arises when there's lots and lots of little things adding up, lots of little effects accumulating. So you might think that the way a given grain of sand ends up being the size that it is the result of a stupendous number of collisions. So remember what I said before about the dog that didn't bark, and you have to go looking for things. So he looks at this and you'd think, yep, that's a pretty close fit. We might as well just say, sure enough, it's Gaussian. And then he had the genius idea that with this amount of data, instead of just plotting an empirical histogram, you can plot the log of it. You've got so much data that you even get accurate measurements in the tail. And here's what he found, right? So there is the dotted line, which would be the log of the Gaussian distribution, right? So its density is of the form e to the minus x squared. You take log of that, it's minus x squared. It's a parabola. What does he actually find his data looks like? Look, straight lines, little curve there, straight lines, right? It's surprising. And it, after many years, there's various fancy arguments as to why this is, but the curious thing is that this was the paper I came across in summer 1983, The Nature and Correlation of Random Distributions. Here's a whole stack of different data. Here's the distribution of personal incomes of Australian residents in 1968. Here's the frequency of dictionary words of a certain number of letters, right? Over and over again, he sees this phenomena where you end up with these exponential tails instead of doubly exponential tails. It's one of these things you have to bother to look. That's the takeaway lesson here, right? If you don't take logs, you won't see it because it's right out there in the tails. And is it significant? You might think, if it's in the tails, it doesn't really matter. But lots of times, right, what you're deciding upon is a tail event. Right? Suppose you wanted to work out the probability that there'll be a cyclone stronger than your building can withstand. You go and get all of this data, you say, it looks kind of normal, I can work out the tail probability. If your tail is e to the minus x squared, it decays very fast. If it's only e to the minus x, it's much heavier. It can make a big difference. But remember, the key thing is you have to know what to look at. He went further, right? Once you're on a good thing, you stick to it. You might have come across this thing. It's called the Galton board or the quincunx. I don't know if you've ever seen this before. The idea is that you have a whole stack of little balls. You tip them in up here. So this is it upside down, right? You then tip it over, and they all fall through here, and they hit these pins. And the idea is that when it hits these pins, there's an equal chance that it goes either side, right? So it's like a whole stack of Bernoulli trials. And then you add them all up. And, you know, if you go and search for this on the web, you'll see a Galton box showing a normal distribution, right? You can go and buy one of these, right? Quants on Wall Street have them on their desk. Seriously, right? It's like, this shows you that the normal distribution is always there. So people do this, and look, they don't really go out into the tails. So our hero, Major Rafe Bagnold, when he retired, he had a lot of spare time on his hands, so he went and built one of these. This is based on 6,000 measurements. I'm going to do the arithmetic on how long that would have taken him. And here's what he gets, right? So that's not explained why that is, but like what I appreciate about this is that he didn't just take it for granted. He said, well, I'll go and measure it myself. Right? You can just imagine his wife saying, "You still in the shed, dear?" "Yes, I'm still doing more measurements." Anyway, you get this here. So, like I said, I read this in 1983 and it's stuck with me ever since. Whenever anyone says, "Oh yeah, the Gaussian distribution, you know, it happens all the time," you think, well, what about sand? Surely it's going to work on sand, but it doesn't even work on sand. Okay. So now we're on a rocky stream, we're back in the promised land. And I want to just briefly mention the reference class problem again. We already met this in a previous lecture. Remember, I pointed you to Alan Hayek's paper, The Reference Class Problem is Your Problem Too. And in the tutorial for that week, I managed to remember and share this paper that I've drawn your attention to explicitly here. Is it a crime to belong to a reference class? Right? So, briefly, for those who weren't in the tutorial, this was a legal case where the penalty of someone convicted of drug trafficking, like they found drugs on him, and then the penalty had to, in law, be proportional to his career total of drug importation. And so then a statistical inference was made, and that statistical inference critically depended upon what reference class to put him into, right? So why this is interesting, you can't have a probability without a reference class, right? It's the group that you're associated with, and we're going to talk about that at length in the next lecture. In this case, this fellow's future life critically depended upon which reference class he was going to be in. Whether he went to prison for 10 years or 3 years, it was like something like that order of magnitude difference, depended upon that. So it's an easy read, and you know, it's a bit of a detective story. It's kind of interesting. There's a few pointers here for those who are interested in how you might try to think about your data in a way that doesn't presuppose a distribution. So I have to say, this is extremely preliminary stuff, right? I mean, I found this kind of interesting. This was by this paper here, Data as Monads, how digital data can be understood as the sum of components in the process of locating it. This was a paper written by a Danish anthropologist, and I think it's quite instructive. So she got involved in a project. I guess there was more quantitative people involved as well. They wanted to understand something about the drug taking habits or the unsafe sex habits. I don't know, something spicy about Danish teenagers. So they did, they went out and gathered data about teenagers going to parties and so on. And of course, some of the teenagers were a little wary about this data being gathered. And so there's a story here about the adversarial nature of the data gathering exercise, right? You're trying to get data about something that people might not want to know they might not want you to know about. And in the end, you end up with some data. But what she went and did was she spelt out in detail this whole process of gathering it, right? So I draw the distinction between all of the other papers that you see. I quoted some of them. Suppose we've got some data drawn from blah. We've just got the data, right? This lady spent quite a few pages describing all of the efforts that she had to go and get the data. Now, what you do with all of that extra information she's provided, I simply don't know, right? I mean, I can't go and tell you how can I convert her prose into a modified mathematical theory that takes that into account. You can't do that. But what I would claim is that it seems unreasonable to ignore it totally, right? It's very clear when you go and read her particular example that if you instead had just said, oh, we got this data, we sampled data from Danish teenagers, IID, great, now let's do some arithmetic, that would be very misleading. Anyway, that's the point of this. There's another line of work, which again might be of interest to some of you, that goes under this rather grand phrase, the sociology of quantification. So this is a summary of this. So it's about the question, we want to understand people in groups, otherwise known as societies, and the way we're going to try and do that is numerically, right? We're going to turn it into numbers. And then the big question is, which numbers, how do we go about doing that, and what are the implications of doing so? So depending upon your background, you might find that interesting. Here's another one with a similar, the title gives us away, What's New with Numbers? Sociological Approaches to the Study of Quantification. So I find this literature interesting because the questions that they grapple with, they're complicated, they're diverse and very rich, but they're usually invisible from the normal ML perspective. So, it's really just, I said that the middle part of this course is just making life more difficult for you. This is just another way of doing that. I want to return again to this ex ante and ex post distinction in a very particular way as a way of trying to understand this notion of sampling. So I already said in today's lecture that the standard incantation that you make is you posit there is a distribution and then you draw samples from it. So let's just think about that in a particular way. So this is what I just said, right? So we the way we understand the relationship between the single event and the distribution is in this phrase, we draw a single random sample, okay? Now, no one tells you how to go and do this, right? But it's a standard phrase. It's not like you're required to do this. It's rather, this is the justification that you state for treating your data in a particular way, right? It's not a method, it's an excuse. Maybe you could put it that way. So the question that I want to ask, right? So I can't tell you that. No one can tell you how to go and do that. But maybe we can illuminate things a little bit by looking at it backwards. We could go and say, how do you convert a single event to a probability? Right? I mean, it's one thing to say, most of you probably aren't too uncomfortable with the idea, here's a distribution, let's draw a sample from it. Okay, we do that all the time, even though you can't explain it in detail. I'm asking instead, how do you go the other way around? Let's think of a single event and turn it into a probability. How would you go about doing that? So the commercial answer to this, if you're a businessman, is you take out insurance. That is what insurance does. That's precisely what insurance does. If you look at a pure insurance business, so with no profit margins, perfectly calibrated, the cost to insure a single event is the envisaged loss of the event times its probability. Right? So if you want to work out the probability that your house will burn down, work out how much it will cost to replace it, then go to an insurance company and ask how much will it cost to insure it, do a calculation, you have the answer, right? Because that's their business, right? That's their business model. What's intriguing is that a lot of the headaches that we've been grappling with fair machine learning have actually already arisen in insurance. Insurance has been around for ages, hundreds of years, right? The merchants in, what's the name of the city? Venice, right? Venetian merchants invented the idea so that, if they lost one ship, they wouldn't go bankrupt. They'd spread the losses around. And I'm talking about, if we think of ideal insurance, which is no social engineering, it's no social redistribution of wealth, it's really just this pure probability play. So, here's this claim, the entire insurance industry is founded on conditional independence. Recall the claim I made earlier in this course, all of these notions of fairness are built upon conditional independence. That's why we had to understand what independence was. There's a complication with insurance. So there's this, what I call the pure notion of insurance, where we actually capture the actual price. But then most real insurance markets come down to also at the same time they try and do some wealth redistribution. So medical insurance is a good example of this. If we looked, if I could go and get a doctor to give you all a checkup, right? And I asked the doctor to just give a single score on general health, right? I don't care how he does it, right? General healthiness of you. It's not all going to be the same. Some of you are going to be perceived to be more healthy than others. And then if we said, let's go and sell you some health insurance. So there's at least two choices that we have. We can either charge everyone the same amount, or we can charge the people who the doctor says are less healthy, we can charge them more, right? And both, hopefully you can see merits in both arguments, right? Anyway, that question of, how do you resolve that and what is a fair way of doing this sits at the heart of all of this literature on insurance. And it's not too hard to see, I hope, that you see that this is very much like the questions that we grapple with fair machine learning. We view the population in terms of statistics. We don't actually care about the individual. The insurance company doesn't have to care about the individual. It has to pay out to individuals, but all of its calculations are in terms of aggregates. Yeah?
Can you explain again where this conditional independence comes in this insurance scenario? I don't understand it.
So essentially, it's spelled out a little bit in detail here, right? And this is where I got that from. But the point is that your model of individuals is that they are essentially, generating random outcomes that you have an insurance contract for independently. So I go and insure your life. I'll go and work out what's the probability that you get cholera, right? You get cholera insurance, right? So in Germany, it's very low. It's not going to cost you very much. Likewise for everybody in the class, right? But then it turns out that the water system wasn't well maintained, and for bizarre reason, the water in Tübingen gets infected with cholera, right? So that would be an example where the insurance company loses out. Normally, they presume these things are done independently. That's how they manage their risks, right? So that's all I was getting at. Anyway, so there's some interesting lessons that you can draw from insurance, and I draw your attention to this paper. So this is Chris Froelich, one of my PhD students. He's written this paper, Insights from Insurance for Fair Machine Learning, and we're interested in fair machine learning. Chris digested a lot of this literature on insurance, and he drew a small number of lessons from that, right? So you can look at this, and it's kind of interesting. And why do I think machine learning can learn from insurance? Well, for a start, as I said, insurance has been around for a lot longer. It's a much bigger business. So if you think of machine learning underpins advertising, that's the biggest business machine learning underpins. That's 2% of global GDP. Insurance is 5%. So it's 2.5 times as big, right? Insurance directly grapples with the aggregate individual problem that we talked about. The fairness concerns are quite pervasive, right? About, in EU law, it's illegal to discriminate insurance prices on the basis of sex, including for life insurance. This was seen to be, a win, right? Gender equity. Why should there be any difference between the price that men and women pay? That's the logic of it. But here's the interesting thing. On average, women live longer than men. What's the consequence of that? The women subsidise the men. So in that little nutshell, you've got a nice conundrum, right? You can say, oh, yeah, we want to be fair. We want to treat everybody equally, right? Fair treatment doesn't mean fair outcomes because the underlying distributions are different. We saw that in machine learning. So yes, it's a useful analogy. So these are some of the points that are in Chris's paper. I'll let you read that if you want. But I just want to flag this last one. So this has all become quite topical of late. So not many people have tried to learn from insurance and apply it to machine learning. What a lot of folks are trying to do is they're saying, oh great, this new technology of machine learning, we can now make insurance better. We can make it more personalized. Rather than charging everyone the same amount, right? Let's take a real example, which I think I've got papers that refer to this. Let's talk about car insurance, right? So insuring yourself against an accident. And so what is now not uncommon is that the price you pay for insurance is a function of how you drive. And how does the insurance company know how you drive? When you sign up for a contract, they send you a little box that you stick in your car. It's got accelerometers and a GPS in it. It can work out how well you're driving, right? It works out how much you accelerate, whether you break the speed limit, because it knows where you are. It knows all of the speed limits. And the bill that you get each month depends upon how reckless a driver you are, right? So, you know, it's kind of obvious that it's got a lot of connections to machine learning. So I think there's some interesting things that we can learn there, right? So I think this is almost the last thing that I wanted to talk about today. From causal to causal independence. So they're quite different words that are almost identical. So first, the causal assumption of independence. So I take this title from the paper I point to, Miracles in Statistics, the Causal Assumption of Independence. So this is a slightly weaker or lower level assumption than the one I talked about before. So if you want to do statistics, the first assumption that you need is that there is a distribution, okay? Oftentimes that works out just great. Sometimes it's dodgy. Here we're talking about something more fine-grained, and that is that the samples that you get are independent. Remember the papers that I quoted from a few slides ago where I had snippets from the individual papers? They didn't just assume that the data was drawn from a distribution, they assumed the data was drawn independendently from the distribution. And you need this, right, for most of the theoretical guarantees on how well your algorithm is going to work. And this assumption is extremely widely made, as this quote says, an almost universal assumption in statistical models for repeated measurements of real-world quantities is that those measurements are independent, yet we know that such independence is fragile. So that's what this whole paper is about, right? He looks at a whole stack of examples where the presumption is that they are independent, and then he looks at it more closely and realizes that they're not, and what are the consequences of that? And that can be quite big. So that's something to watch out for. Now, an even more subtle, this is again in the realm of theory ladenness of data-driven methods. So I'm not going to try and go through this in any detail. If you've met this before, it will make sense. You can always look it up if you're interested. So there's a thing called a copula. So you know what a joint probability distribution is. So it turns out that you can always write a joint probability distribution in the form of this yellow equation on the third line. H is the joint distribution, F1 to Fn are the marginal distributions, and C, this function that links it all together, is a copula. And what is this copula? It itself is a joint distribution, but with uniform marginals. What's the point of this representation? It's very elegant. What it does is it separates, mathematically it separates the two distinct things of the marginal distributions of each variable and the way they're coupled together, right? So, if you have several random variables, you can separately look at each of their marginal distributions. This is an easy thing to estimate reliably. You can easily get your hands on that. The hard thing to do it's the thing that most supervised machine learning tries to do, is to understand the joint distribution. As X increases, does Y increase? Right? That's what's captured in the joint part of the joint distribution. The copula is a way of capturing that dependence that's independent of the marginals. If you have a stack of variables, x1, x2, up to xn, and you do a monotonic transformation on some of those variables. So instead of having x2, I have x2 squared. Let's suppose that they're all positive, so it's monotonic and invertible. Then the joint distribution changes in a complicated way. The marginal distribution changes in a way that's pretty easy to calculate. The copula doesn't change at all. The copula quotients out all of the changes of variables that you make. Anyway, so that's the background, right? Super speedy introduction to copulas, but they are becoming increasingly used in machine learning. But the point is what I've written here in green. The copula captures the dependency information, ignoring the marginal. So if you knew the copula and the marginal distributions, you know the full joint distribution. For very complicated problems, it's easy to get the marginals, very hard to get the joint distribution. People knew of this representation, and so they thought, we want to do this clever stuff, right? We want to do, using clever numerical algorithms, we want to price financial options, but we want to be wary of risks. And we know that the risks might not be independent. We're not that silly, right? We're not as silly as on the previous slide. We know that if this bank goes bankrupt, maybe this other one does too, we will try and capture that. But doing the full modeling, capturing the full exact copula, is too difficult. And so what people did was they introduced this thing called the Gaussian copula. This is the copula that a multivariate Gaussian distribution would have, but using it as a copula allows you to have the marginal distributions not being Gaussian. So it's this halfway house. It's halfway in between having a completely arbitrary distribution that's impossible to work with, or just assuming a multivariate Gaussian distribution which clearly doesn't fit the data. You can see that on the marginals. It's a clever compromise, right? So people worked out how to do the clever option pricing when the various assets risks were governed by this joint distribution with a Gaussian copula. And, that seemed a fine thing to do. So it became very widely deployed in financial institutions, particularly in Wall Street. And interestingly, when people say doing maths doesn't have any impact, well, here's an example like this. How would you feel if you were the guy that invented this thing and then everybody adopts it and it is then responsible for a $2 trillion loss? Because that's essentially what happened, right? So there's this nice story. So I repeat, this is a little bit of a digression from our topic, but this article explains this recipe for disaster, the formula that killed Wall Street. I'm presenting this as another example of, theory-ladenness or, more to the point, the use of a method, the presumption that the theory holds in a situation when it doesn't, and look at what the consequences are. So, no, this is not strictly machine learning, but then you might say that it is. After all, there's a lot of machine learning jobs on Wall Street. I've had students go off into this. One of them ended up running his own hedge fund, right? Using machine learning models. So this stuff is consequential, and the huge negative impact that you see here caused by a very benign looking assumption. I think it's worthwhile keeping that in mind. Right, I don't think I need to say any of that. Okay, so as I said, a little bit of a digression, but going home for Christmas, and if any of your relatives ask you, how's all of this math stuff have an impact on the world, you've got a good story by the fire. So that was the casual assumption of independence. Now, the final thing I want to talk about briefly is causality. So everything we've spoken about so far in the course, we've used the usual probabilistic machinery, right? The measures of fairness we introduced in the first lecture were described in terms of statistical independence. And we had ways of quantifying that. And we built, there's many things that you can do there. But, it's a common story. People say, well, statistics can only ever detect correlations, but what we really want is causation, whatever that actually means. And you can check if you just do a Google Scholar search. Here I did one a couple of weeks ago, fairness causal. There's lots of papers on this where they say, yeah, the problem is that we're just treating this question of fairness in a purely statistical fashion, whereas we need to go and, we want to find the true causes of fairness, right? So there's a very large literature on this. My first objective is to simply point that out. But I do want to challenge the idea that this will actually make significant progress. All right? I've really only got one point I want to make here, and that is, why are we so convinced of the power of causal reasoning? There is a nice paper I've put in the shared readings called Causation as Folk Science. Most scientists don't talk about causes, right? They talk about, control problems. They talk about how things are related. They make explanatory models of the world. But you go and look at a typical scientific paper, they don't go and use the word causes. And Bertrand Russell observed this long ago, right? He said, this was, I think, 1913 he wrote this, the law of causality, I believe, like much that passes muster among philosophers, is a relic of a bygone age, surviving like the monarchy only because it is erroneously supposed to do no harm. I mean, he's in a minority still. There's many people that still believe this. It's baked into our language. When we go and try and explain the world, how the world works, certain aspects of the world, our language is intrinsically causal. When we want to go and blame someone, put them into jail, we're definitely doing causal reasoning, right? And so when we go and think of, here's this machine learning system, it caused this harm. See the language I used? It caused this harm. You can't avoid doing it. We think in terms of causes all of the time. So we tend to see causes everywhere, even if they don't exist. Right? So this paper, Illusions of Causality and How They Bias Our Everyday Thinking and How They Could Be Reduced. So some people have started to think about, how can we be a little more wary about this? So there's this nice book, if you're interested, The Neuroscience of Our Addiction to Stories. So the way our brains work, like I don't know if you know this, if you want to remember a big stack of things, like a shopping list, and you can't write it down on your piece of paper or your phone, you just have to remember them. Standard mental trick, I learned this as a kid, you turn it into a story. You make up a story with all of those elements and you will be able to remember the story. Our brains seem to have evolved to remember stories very well. Consequently, when we go and look at the world, we look for stories. We look back at history. We say, why did this happen, right? We want to find causes. So that's the point of this book, how history gets this wrong, right? This author argues that, when you go and read a history that says, oh, the real reason, I guess that's Napoleon, why Napoleon went round riding on his horse, doing the damage that he did, was blah, 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 right? Gives you a nice, simple answer. The reality will be a lot more complicated. I guess all I'm saying is that be wary of going down this road with your machine learning models. I don't really have time or the knowledge to look at that more closely. I did just want to essentially acknowledge that there is that line of work on causal machine learning. I've already moved on from the slide. One thing I did want to say was, if you say, well, what would you do instead? This is worth saying. So suppose you have some social problem, right? You go and measure with your machine learning algorithm. We see this very strong correlation between this and that. This is this undesirable state of affairs. I don't know, the more people living in poverty in an otherwise rich country. And you want to understand why that is. And so people will say, we want to understand the causes of poverty. But then you ask, why do you want to understand the causes? Right? Is it just because you're interested to know? Most people would say no. The reason you want to understand the causes is so that you can do something about it. So I would argue that any time that you frame your problem, your data-driven problem, particularly to do with people, any time you frame that as a search for causes, I can reframe the problem directly as a control problem, right? I can state my problem without using the word cause at all. So instead of saying, I want to find the causes of poverty, I could just say, I want to design interventions that reduce poverty. I don't need causes. Control engineers, I used to work in a department of control engineers, and there's a textbook I remember looking at. It's like an undergraduate textbook that teaches you the basics of control engineering. The key thing about control engineering is that they grapple with systems with feedback loops, like the chicken and the egg, right? You know, the system behaves this way, the airplane flies up a little bit, the altimeter measures that, it feeds the signal back to the elevator, and it makes the plane go back down again. And so the question is, the point is, in a feedback system where the output is fed back to the input, using the word cause doesn't make any sense. It's literally that same question, which comes first, the chicken or the egg, right? They're codependent, they're in a causal loop. Let's not use that word. In this book, they say this on page 2. They say, look, this whole cause thing, it ain't for us. But the good thing is we don't need it. And for the next 500 pages, they go on and tell you how to go and design ever increasingly complicated control systems without introducing the notion of a cause. Okay, so that's the longer reason why I introduced this. So there is an alternative, and that's why I'm not trying to do the causal story in this course. So what do we do today apart from finishing way early, about the same amount early as I did finish late last week, so mission accomplished. Persistently recurring mythology of machine learning is that it avoids theory and represents a new theory-free paradigm of science that avoids the prejudices of the past. This just recapitulates the prejudices of the past, ironically. Data and all of its downstream products, in particular distributions, are theory and value laden, and the mere presumption that there is a true distribution is one of these theoretical presumptions. I reiterate this point, you should not merely look at the ethical problems that are apparent to you, you need to look at what you don't have, right? What you don't gather. The data on people that you did not measure, right? What are the implications of that? These underlying, let's call them meta theories of statistics, that there is a stable distribution, that the examples are drawn independently. This is extremely widespread. It's implicit. It's usually stated in, line 1 of section 2 of the paper. That doesn't mean that it's not a theory. It doesn't mean that it's not consequential. It is something that you can challenge and pay attention to, but you have to remember to look, right? Remember the analogy of Rafe Bagnold with the non-normal distribution. He had to go looking for it by taking the log of the density to go and see it. I don't need to say that about causes. And I think, nevertheless, notwithstanding all of that I've said, I think the most insidious theoretical assumption is hidden in the categories or labels that we use. So this is essentially the reference class problem. Where do the labels come from? And I'm going to manage to talk for an entire lecture about that in lecture 10 in whenever we meet again in January next year. So that's it. Thank you. Have a good break. And if you feel free to write to me with questions about the essay, I'm happy to receive that. I don't promise I'll respond, but I'll endeavour to do so.